What I do know is that today we're starting chapter 14. So here we go. When we look at it, we did gas laws so we could understand what was happening with molecules in motion in a gas. Chapter 14 is about heat and how we can transfer energy from one object to another due to a difference in temperature. Where we're going to wrap it all up is that in chapter 15, we are going to see how that heat transfer can do useful work. Chapter 13 and 14 are similar to things that you studied in chemistry. Chapter 15 is when we get to throw in the physics. So I went pretty quickly through gas laws. I'm going to go pretty quickly through heat. We'll see how you do. And then we'll really tie it all together in chapter 15. So with that said, how about you take out a nice clean sheet of paper? I've got some notes. I wrote these out last year, and you know what? They're still good. So I'm going to use them. How about you write them out as I talk? And then I've got 2 videos for you. Ms. Wu will talk about the 3 ways that energy is transferred. She does a beautiful job as always. And then Mr. Anderson. Today is about getting some basic vocabulary down. Monday, we will start doing some mathematical examples, and that's usually when it starts to gel and come make sense. So, you got that paper out? No, you don't. Get it out. Here we go. Number 1, we got to define 3 things before we get too far here. 1, we've got to define heat, temperature, and internal energy, because although they all sound like the same thing, they're not. Heat. We utilize the symbol capital Q for heat. You may remember that from calorimetry last year, or in chemistry 2 years ago when you did a little Q equals MC delta T. Yeah, does it look familiar? So heat, we use a capital Q. It's not charge, it's heat. Now we measure heat in joules, but heat has a very specific definition that I think we sometimes butcher in English. In physics, heat is the flow of energy due to a difference in temperature. Heat only flows from a region of high temperature to a region of low temperature, never in the opposite direction, never. Heat flows due to a difference in temperature. However, heat is not temperature. Nope. Those are different things. Do not use those 2 words interchangeably. Temperature, we use a capital T. Duh. It's measured in kelvins. And it's a measurement of the average kinetic energy of the molecules. Now, in a gas, it's much more obvious that kinetic energy is translational, meaning it's moving around. Gas molecules moving all over the place. In a solid or a liquid, it's going to be the vibrational kinetic energy when it's locked in as a solid. It's hard to do this on camera. There they are. And the higher the temperature, even as a solid, they're going to have more vibrational kinetic energy. In a liquid, they can roll all over each other. Just trying to make something that's easy hard. Temperature is a measurement of the average kinetic energy of the molecules. Lastly, internal energy. U, this is the big one. This is the one that's really going to come into play with thermodynamics. We utilize the symbol capital U for internal energy of a gas. It's measured in joules, and it is the total kinetic energy of the molecules in a substance. Now, that's different than temperature. Temperature is a measurement of the average kinetic energy. The internal energy is the total kinetic energy in a substance. In a gas, we showed last unit that U is 3/2 nRT, or it could be 3/2 PV, but the real key is the internal energy is related to the temperature. And if I were to add one thing in as a little bit of foreshadowing, the change in internal energy would be proportional to the change in temperature. So if something's isothermal, what's the change in energy? That's right, Abel. It'd be 0. Nice job. Good. Check it out. But for your notes, I'd like you to write down this. 3 ways for heat to be transferred. 1 is by conduction. Now, conduction, there is a relationship, delta Q over delta T. So that would be the change in heat per unit time is equal to K times the area times the difference in temperature, all divided by the length or the distance. Sometimes you may want to consider that a thickness between two materials or two temperatures. Ms. Wu is going to do a beautiful job. Write that formula down. K is simply a constant. It's a physical property of the material. Different materials have different K values. For example, silver has a higher thermal conductivity than aluminum, which is much higher than concrete. There's a pecking order. And its rate of conduction would be, it's a similar property as when we talk about electrical conduction. Now, conduction and the heat being transferred is really a transfer of energy due to collisions. Second type of ways, or second way that heat can be transferred is by convection. And that is the mass movement of molecules. Let's see. It's cold outside. Now the cold air is coming in, the warm air is going out. Heat is being transferred to the outside by the molecules actually moving out the window and increasing the temperature outside. Obviously, by a very small amount. If you have forced hot air as a heating system in your house, that's using convection. And lastly, radiation. Radiation is the transfer of energy in the form of light. We gain energy from our sun in the form of light. I even wrote down there E equals NHF. We can think of it as that energy of a photon. All right. Now, I also want to throw this out there. Sort of this is my little intro transition to the next unit. We got to go back to chemistry a little bit. Remember these? At the time, they seemed difficult, and I think when you do them now, you'll say, "Wow, why did my sophomore self ever have difficulty with these? This is a piece of cake." If I take some hot metal that's at 100 degrees Celsius, and I put it in a bath of water at 20 degrees Celsius, what's going to happen? The water gets warmer because heat's going to transfer from the hotter material to the cooler material. Eventually, they will reach what? That's right. They'll reach what's called thermal equilibrium. Mr. Anderson will talk about that in a little bit. Monday, everybody. So here's the thing. When it comes to heat, it's actually not all that complicated. But we do have a few formulas that I wanted to review with you how to use them. You've learned this in chemistry, which for me is a bit of a tricky situation to be in because I think you already know this stuff. But that was a long time ago. You were just sophomores at the time. Not that there's anything wrong with sophomores. Don't get me wrong. Now, just sort of here's my thought. I was going to take you through these notes real quick. And I also PDF'd them. So if you want to push pause, print it, boom, you're good. If you don't have access to a printer or you want to write it, go ahead. But right now, I just thought I'd talk through it quick. So heat. Again, the key thing here is to recognize that heat is not the same thing as internal energy. It's also not the same thing as temperature. Heat is simply the transfer of energy from one place to another due solely to a difference in temperature. Yeah, it's different than what you thought. Now, heat, one way that we can calculate heat is to look at the way it transfers from one object to another, or when that heat goes into a phase change. So here are three formulas that you should be familiar with, and at the end of this, you got to know how to use. So the first is Q equals mc delta T. M is the mass, C is the specific heat of the substance, and delta T is that change in temperature. And just a reminder that the Celsius scale, each step on the Celsius scale is the same as a step on the Kelvin scale. Now, this is what we didn't talk about last time. Q equals mLF. Now, this is the heat necessary for a solid to undergo a phase change into a liquid. It takes energy to get those atoms that are all sitting locked into a matrix to start to move around over each other. You're increasing their kinetic energy when you do that. Now, this latent heat of fusion, one of the bigger misnomers out there, it's not fusion like fusion in the nucleus. You know that, right? It's just the name for when it goes from a solid to a liquid. Now, here's the thing. When a liquid goes to the solid phase, what's actually happening is that amount of heat would be released. So it works both ways. All right. And then the other formula, Q equals mass times the latent heat of vaporization. It's right in the name. When it goes from a liquid to a solid. Oh, man, I was so proud of these notes. And then I clearly wrote liquid to a solid. Oh, my gosh. Let me get back to this. Can I click? Well, sometimes I include these things just so that it doesn't seem like I'm too ahead of the game here. Now, my pen's not working, of course. So that is going to be gas. If you guys could. I'm going to push pause, get my system up and running. All right. Well, that was embarrassing. So here's the thing. Q equals mLF or Q equals mLV. LF and LV are just constants that you would look up in a table, just like the specific heat. And it has to do with the material that you're looking at. Now, in a bit of foreshadowing, I'm throwing out the first law of thermodynamics for you. This is chapter 15, but this is what it's all going to boil down to. And basically it says is that the change in internal energy of a gas is equal to the heat added to that gas plus any work done on the gas. Now, if you read ahead in the chapter 15, you might see the signs are different. Don't read ahead. Don't do it. Well, yeah, you might not have anyway. But there it is, the first law of thermodynamics. Oh, that's awesome. And last thing I needed to hit on from chemistry. Calorimetry is all about the sum of the heat of the system is going to be equal to zero. If heat flows out of one substance, it flows into the other. We are, in calorimetry, we are always going to assume that there's no interaction with the environment. Another way to put it would be to say it's thermally isolated. We don't deal with the heat loss out. Now, I bring this up because it's actually very easy, but chemistry and physics sometimes treat it slightly different. If I take a sample of metal, let's say it's copper, often we can heat it to 100 degrees Celsius. Why is it always 100 degrees Celsius? Oh, because you can put it in boiling water, which is at 100 degrees Celsius, right? Heat will flow into the metal until it also reaches 100 degrees Celsius, and then heat will stop flowing. You take that hot metal, you put it into cold water. What do you get? Warmer water. Heat will flow out of the metal into the water until thermal equilibrium has been achieved. Oh yeah, Mr. Anderson talked about that. Now what's the deal? Well, in physics and chemistry, we may treat the signs slightly differently. And I've been arguing with students about this for years. Actually, I've been arguing with Mr. Nash, and students are caught in the crossfire. In the end, you can do whatever you want. Heck, I don't even get to see you anyways. But here's the thing. In physics, we say the sum of the heat is equal to zero. And this sigma, gosh, we've been talking about it for 2 years now, means the sum of. Now, heat is not a vector, it's a scalar. So when I add them together, I actually just add the heat gained plus the heat loss equals zero. I know the heat loss will end up being negative. I get it. Now, I do a little bit of algebra. I bring the heat loss over to the other side. And because of the way I usually say it, I would say the negative heat loss is going to be equal to the heat gained. So I just changed the order. Oh, no big deal. Now, when I look at my formula, M of the metal times the specific heat of the metal times the change in temperature of the metal equals the mass of the water, specific heat of the water times the change in temperature of the water. Now, when you do change in temperature or change in anything in physics, it's always going to be the final minus the initial. That's where my hang-up is. So that when I plug in the numbers, like the example up above, I would write it as 35 minus 100. Because the final temperature of the metal is 35, and the final temperature of the initial temperature, of the metal is 100. Yeah? What's going to happen to that value? Well, I know that you know it's negative, which then cancels out with negative at the beginning, and everything is hunky-dory. All right. Now, in chemistry, you did this. Now, is this wrong? No, especially not for a sophomore's mind, who gets confused anyways. But let's just look. You jumped right to Q lost equals Q gained. Okay, we'll ignore the signs. MC delta T equals MC delta T. All right, that's cool too. But then this was the trick. What you guys did was you always subtracted the temperature and just made it so that it was always positive. So on the metal side, you would do the initial minus the final temperature. And on the water side, you do the final minus the initial, so that both were positive. Means when you plug in the numbers, you get that. Does it work? Absolutely. Why do I get hung up on it? I don't know. I think it's about the delta T thing. Some years I just give up and I just go with the chemistry way. Some years I hold fast and do physics. I might do it both ways. Do you guys even care? No. This is all about my hang-ups at the moment. I just had to get it off my chest. You guys do whatever you want. Hope you're okay. I'll start the examples in a few.